In today's video, we are going to be talking about transformation properties. Now, before I get into the transformation properties, I want to go through what we call rigid versus non-rigid motions. Rigid, and then we'll zoom this in a little bit. We will do rigid versus non-rigid. Now, what are the two, right? Let's start with rigid. Now, a rigid motion preserves length, so it preserves length, angle measure, shape, area, parallel and perpendicular lines, and midpoints. So rigid motions would be your translations, reflections, rotations. When you do these type of transformations, these are all of the components that will be preserved in that rigid motion. Now let's talk about non-rigid motions. A non-rigid motion is a transformation that changes the size of a figure. So your most common non-rigid motion would be dilation. In this non-rigid motion, it's going to have slightly similar, slightly different rule sets. So angle measure is preserved, shape is preserved, and parallel lines remain parallel, just parallel. So when it comes to like your area or your length, depending on how you scale it, it may be greater, it may be less. So now that we have gone through these type of motions, let's actually see them in play. So here I have different transformations, right? And so first, let's identify this one. This one, it looks like we are just sliding the shape down. So this would be our transformation. So here I have 5 different transformations, and I want you to pause the video and see if you're able to identify which transformation is which. All right, now that we have taken the time to do that, let's go ahead and go over it. So for this first one, I see that we are just sliding the shape down. So this looks like it will be our translation. This one, if I were to put a line of symmetry through, like so, and then reflect it across this makeshift y-axis, then we get the same shape over here. And so this would be our reflection. Next, it looks like if I were to rotate this shape 180 degrees, so this is now this point, rotate it 180 degrees would come here, right? So that's going to be our A prime. If I take this, it's going to be our B, and rotate it 180 degrees, it'll end up right here, which is right here. That's our B prime. And then take C, rotate it 180 degrees. It'll end up right here. That's our C prime. So this does look like it will be our rotation. And then, oh, I see that I have accidentally put 2 rotations on here. So yes, these are both rotations. If I were to take this shape, and it looks like the center point for rotation, or the point of rotation, would be somewhere over here, and then just rotate this shape down. Then I would get from the pre-image A to image B. And then last but not least, we have a bigger shape here, and then we are kind of scaling it down to a smaller shape. So from A to B, we're taking the bigger shape, making it smaller. So this would be our dilation. And so I want you to just take a look at these different shapes and kind of think back to the properties that I just explained previously. We see here that for translation, reflection, rotation, our non-rigid, or our rigid motions, that the shape is still intact. Everything is all in order. It didn't change length. It didn't change angles, anything like that. And then when it comes to dilation, when we're scaling these, when we're scaling the area or the length of the shape, let's say this is like 6, right? So we'll do 6, 6, and 8. We then scale them down. Let's say we scale them down by half. So this is now 3, 3, and 4. So even though the area gets smaller and the length of the sides are smaller, the shape is still the same, the angles are still the same, and overall the shape is still the same.